A maximally stimulated muscle fiber develops its greatest tension or force at 1.2 times its resting length due to active and passive components. As a whole, a given muscle's tension responds to length as well as muscle architecture. We cannot say that EMG is the same as force, since the cycle of depolarization lasts 2 milliseconds, and maximum mechanical contraction forces are achieved between 20 to 250 milliseconds after depolarization. Yet there is a positive correlation between EMG and force. Active insufficiency happens when a multi-joint muscle cannot contract at its maximum force due to its shortened length. My question is there less percentage of maximum voltage generated by motor units when a muscle is in active insufficiency? Several assumptions are needed to make a hypothesis. 1. The length tension model holds more power for the muscle than the architecture of that muscle. 2. The motor unit electrical potentials positively correlate with force. And 3. Muscles in active insufficiency will generate less force. Therefore, the hypothesis is that the percentage of voltage of maximum voluntary contraction should be lower in muscles in active insufficiency compared to antagonistic muscles in lengthened positions. Peak voltages of maximum voluntary contraction on a dynamometer were obtained for 8 participants for the wrist flexors and extensors for a comfortable position, long hand grip, short hand grip, wrist in maximal extension, and wrist in maximal flexion. According to Figure 9, for long hand grip, the extensors had a higher mean percent MVC EMG than the flexors. For short hand grip, max wrist extension, and max wrist flexion, the flexors had a higher mean percent MVC EMG than the extensors. The hypothesis was not supported since the flexors have the greatest percent MVC EMG during what would be active insufficiency or max wrist flexion. It's possible that any of the 3 assumptions made for the hypothesis were incorrect. For the second assumption, it is possible that when the muscles were in active insufficiency, there was more excitability of the motor units, even though this may not have translated into a higher mechanical flexor force. Figure 10 shows how the peak force of the flexors is significantly larger than extensors in mean long hand grip, mean extended wrist, and mean flex wrist. According to Halbeck, the force of the flexors is much larger than the force of the extensors since the forearm has been optimized for strength and flexion. It is possible that even in active insufficiency, the firing of the flexors' motor units is generally larger than extensors' motor units due to the evolutionary need for strength of the flexors. Understanding whether the flexors or the extensors have a higher percent MVC during different positions can be used for a treatment plan of a patient with a wrist joint fracture.